So we already have this expression. So we will now um, uh, gonna express the right side of our equation, which is the energy that is living on the system. So let's consider this one of the Q living. So we have this expression. Say we have Q x plus dx. Okay. So going back, we have our we already have our uh, qx, qy, and qz. But this time, uh, yan. So we have this part, right? So we have our qx, qy, and qz. So this time we will gonna solve for this part. But we need to for I mean for this certain kind of expression, we need to do some mathematical techniques. So if we have expression like this, then we can use the what we call the Taylor series expansion. Yan. So we have the what we call the Taylor series expansion, wherein if we have a function of say x plus its derivative dx, then we can expand this term by having the function of x. So this is our function. So this is our function. And then plus the derivative of the function dx. Then plus the the okay. Plus this whole term here. Okay. So using the Taylor series expansion of this expression, the series can be this expansion is equal to the sum function plus this term here is the what we call the slope, and then the last terms, this part is the higher order terms. So this whole part here are the higher order terms. Okay. So this is according to the Taylor series expansion. Okay. So using this method, we were gonna find this expression. Okay. So since we have this function that is q x plus dx, then we will gonna follow this Taylor series expansion. So the function of qx is that we have x, right? So we have qx and then plus the derivative of the qx dx, right? And then plus the higher order terms. So for this certain type of equation, we will gonna hold y and z constant. So we're gonna holding y and z constant. So we will be dealing on x alone. So we will gonna hold y and z constant, thus neglecting the higher order term. So we're gonna neglect this part. Okay, so we're gonna cancel this out. So we're gonna cancel this last term here. Okay, so we only have this now two expressions: the function, this part, and the slope, this part. Okay, so substituting the values of our qx, so we have substitute value. So when we're gonna substitute our qx is, we already have qx, right? So this part here, wherein this is equal to this part. Yeah, this part. Negative k a dt dx. Negative k dA, which is dy. So k, negative ka t over dx, right? So that is our qx. And for this expression, we have plus, again, the negative k a yeah. So we have this term, right? So we have the qx, this part, and the derivative of this q. So we have this, and yeah, that's all. Okay. So simplifying this, we have x plus dx. We have negative k dy dz dt dx minus, so let's take the negative sign outside. So we have negative e x k dy dz dt over dx d of x, right? Okay. And yan. Okay. So we can furtherly simplify this by having our, say we have k what else, dy dz partial derivative of t x d dx k dy dz, sorry, let me dt over dx, then let me write this term at the end of this expression. So right? So I've only arranged the terms, so we have these uh, expressions, okay? So we have this part, negative k dy dz, partial derivative of t with respect to x, minus this partial derivative of this term with respect to x also, okay? So we use the partial derivative because um, we only deal with the variable x, okay? So let me box this part. Okay. So having this expression using the Taylor series expansion, we can also adopt this. We can also adopt this form. I mean this mathematical technique in y and z direction. Okay, but first let me um, use it for the one direction only for x. Okay, so that later on you can adapt it in y and z. Okay, where are we? Okay, we are here. So let me copy this part. So we already have this expression, right? And okay, and we've I mean we already solved the left side, and like what we have said, we are now dealing on this right side. So this q dot x plus dx is now equal to this one, right? So we will gonna substitute this whole term here in this portion, okay? But before that, in order for us to um, easily simplify our equation, then sorry, okay, let me erase some lines. And okay, look at this part here. Look at this part here. So our q of x is this part, right? Okay, and if you notice this part here, we have a negative k dz dy partial derivative of t with respect to x, is that we have a similar term here in our expression of the q x plus dx, right? So we have the similar expression. So let's check if we can cancel this out. Okay, so considering only the x, so our qx equal to q x plus dx, right?